In this segment, we're going to talk about traveling waves, waves that move in position, but also in time. So when we're thinking about simple harmonic motion, the mass moves in position. It also has a time component. Its position is varying over a course of time, but that wave doesn't propagate out from a source. We're going to think about that first by thinking about waves on a string. We're going to send out a pulse. So a transverse wave pulse traveling along a stretched string is shown down here. Okay, so we give the string a little flick. Okay, and then we get this little peak that travels forward. Okay, in time. So the curvature of the string due to the wave leads to a net force that pulls right here a small segment of the string either upward or downward. So right here at this point, we're zooming in here, we've got a net force that's pulling upward on this string. And then that's going to cause that point to move up in amplitude, okay? But then the wave itself is going to move forward, okay? So what happens is that you send out this wave on the string. It's the material that's oscillating up and down, but it's that wave that's moving forward. So this little particle doesn't move forward in position or in time. It just moves up and down right here from where it was sitting. So as that wave passes through, that particle just moves up or down, but the wave itself as a whole keeps on tracking through the rest of the string. Okay, so here's another PHET simulation, and I'm going to send out a little pulse on this wave on the string. Okay, we're going to send out a little pulse. I'm going to give it a maximum amplitude. Okay, so you see these particles move up and down as that wave form or that wave shape travels. And with this, let's put this in slow motion. With this traveling wave here, since we've got a fixed endpoint, that wave travels through, it hits that fixed endpoint and it gets reflected and it's upside down on its reflection back. Here we have another example. We've got a wave traveling on the surface of water, okay? So our wave is going to travel with some speed along the surface of the water. The water particles oscillate up and down. It's the wave that moves forward. Okay, so the energy in the wave propagates in the direction the wave is traveling. Propagates means moves. Okay, but the components of our wave don't move. So we think about this wave as it's moving along the surface of the water, and we've got this little duck here. The duck is just oscillating up and down on the surface of that water as that wave is passing through. Okay, the water is moving up and down, but the wave that it was sitting on has some forward velocity, and it's going to keep on going. And so the velocity of this wave as it's moving in time is given by the wavelength of the wave times the frequency of the wave. And so we could also, because we know that frequency is 1 over the period, we could also write this as saying that the speed of this traveling wave on the water is equal to the wavelength of the wave divided by the period. So here, this Greek letter, lowercase letter lambda, is what we're going to be using to represent wavelengths of waves. So that's the distance between peaks on a wave is the wavelength, the distance between peaks of a traveling wave. So here in this picture, we're looking at a graph of the position of a wave where the vertical axis is displacement along the y-axis and the horizontal axis is displacement along the x-axis. In this case, we're looking at y versus x here, okay? And so in that case, the distance between consecutive peaks or troughs in our wave is what we call the wavelength. So I find that it's sometimes hard to distinguish the difference between when we're looking at a graph, when we're looking at the waveform. Are we trying to find the period or are we trying to find the wavelength of the wave? And so the important thing is to think about what are we looking at in the graph. So in your graph of your waveform, if you're looking at a graph of position on the vertical axis and time on the horizontal axis. The time between consecutive peaks on the graph is the period. Okay, so you want to think about, am I looking at time on the horizontal axis or am I looking at position? If you're looking at time on the horizontal axis, you're going to think about finding the period. If you're looking at x on the horizontal axis, you're going to think about finding the wavelength. Now, if we're looking at a graph of position vertically on the y-axis and position horizontally on the x-axis, we're looking for the wavelength here. The wavelength in this case is the distance spanned in one cycle of motion. So if you're looking at a graph of y versus x for a wave, the distance between consecutive peaks of the wave is the wavelength. Previously, we had an equation that showed us for simple harmonic motion or oscillatory motion, the position of a mass as a function of time. Now we're going to think about the vertical position of a particle or a point on a wave as a function of the horizontal position at some time t. And that equation is given here. It looks very similar to what we've already seen. So the vertical position y of a wave as a function of its horizontal position is equal to a cosine. And then inside the argument, we've got 2 pi times x over the wavelength. So this was really similar to what we saw for simple harmonic motion, except x was t in that case, and we were looking for the displacement of that object around equilibrium as a function of time. And so here we're looking at any time t, the vertical position of the wave as a function of the horizontal position of the wave. And in that case, along the horizontal axis, if we look for the consecutive peaks, we've got the wavelength, which is the distance between consecutive peaks. So this wave is traveling in time. So this graph down here is this same wave, but at some later time t. And so we see that the crest of this wave has moved in comparison to the wave that we were seeing at a previous time. So now we can combine the mathematical expressions for the displacement as a function of position at any given time and the displacement as a function of time at one position. So what does that mean? Well, now we have an equation that will tell us the vertical displacement of a wave. So what does that mean? Now we have an equation that tells us the vertical displacement of a traveling wave at any given point x along the horizontal axis and at any given time. So now we're combining position and time together into one equation. So far, we have been treating position and time separately for those equations of the waves that we were seeing. So this equation right here, y is our vertical displacement, and it's a function of the horizontal position x and the time t. And so this function will tell us, again, the vertical displacement of a point on our wave, and that equals a, which is the amplitude of the wave, times cosine or sine of 2 pi times x over lambda minus t, little t over big T. Okay, so remember, lambda is the wavelength, big T is the period. Okay, so all of this stuff inside those parentheses is what we call the argument of the cosine. So if you're going to evaluate this function, okay, at any time, you have to calculate what is this stuff inside the parentheses first, and then you put that in to your cosine equation. So there's a lot of math in there that we're going to practice here in a minute. And this image shows us what this equation is trying to do. So on the vertical axis, we have the y displacement of our wave. On the horizontal axis, we have the x displacement of the wave. And then with this equation, we're able to plot what this function looks like at, for example, here, t is equal to 0. Down here at t is equal to 1/4 the period. Down here at t is equal to 1/2 the period. So this equation tells us a lot of information about where we are in space if we know the x position and if we know the time t.
So the equation for a traveling wave in your equation sheet is different than the one I wrote right here. So sometimes we can write these equations in different ways, and I'm going to show you how we can get it into the form that's on your equation sheet, which is also the same form that you're going to see in a workbook problem. Okay, so we'll notice that in this problem, the speed of the wave is not represented. So we're going to change this problem, or change this equation so we can input the speed of the wave in here. So the two things we're going to use in order to help us do that, well, first we've got big T, the period of oscillation here. We remember that the frequency is equal to 1 over the period. So I can replace this 1 over the period here with the frequency. So I can rewrite this argument of the sine as 2 pi times x over lambda minus t times the frequency, because 1 over the period is the frequency. Okay, there. Now we also remember that the speed of the wave is equal to the wavelength times the frequency. Now I could rearrange this to solve for the frequency, and if I do that, then we find that the frequency is equal to the speed of the wave divided by the wavelength. So I'm going to replace f in this equation here with the speed of the wave divided by the wavelength. So then my argument becomes 2 pi times x over lambda minus t times v over lambda. Okay? So I see that both of these terms here have the wavelength lambda. So I can factor it out in front of these parentheses here. So this is 2 pi over lambda times x minus v times t. Okay? And I'm going to write out my a sine. So all of this stuff right here is what we call the argument of the sine. All of this stuff here is the argument of the sine. And so when you're putting it into your calculator, you're going to have to type in sine parentheses, and then all of this stuff in here goes inside the parentheses of the sine function in your calculator. Okay, so that's a lot of stuff to try to stick into your calculator at one time. So I recommend that as you're evaluating these equations, that you kind of do it in smaller chunks, maybe piece by piece, before you type it all into your calculator. Because if you don't have the parentheses in there just right, in the order of operations just right, you're going to end up with the incorrect answer here, and it's all because you've typed things into your calculator incorrectly. Okay, so this and this down here, this line up here and this line down here, are equivalent ways to write this equation for the traveling wave.
Traveling waves add together as they move through a medium, as they move through any material. They can add together when they're moving through the air. That's part of wave optics, which is what we're going to talk about in the next few mini lectures. When the waves add together, when they encounter each other as they're traveling through a medium, we call this superposition, adding together. So here's an example of one wave. And here's an example of a second wave. These waves, let's say, encounter each other as they're traveling through a medium. The resulting wave, or the resultant wave, is just the sum of those waves added together. So you take these waves, you could even give their amplitudes a number, okay? And you add the amplitudes together, and then you end up with the resultant wave. So here we have wave 1, which has this nice sweeping sine pattern. And we've got wave 2, which is this cosine pattern that's has a shorter wavelength, okay? And so when they add together, we're adding up the amplitudes, the sum of their amplitudes all together, and we end up with something that has a little bit of the shape of wave 2 and a little bit of the shape of wave 1. This is superposition. Now, some very special things happen. There are two special types of superpositions that are going to be really important for us as we move forward here. So for example, let's say that two identical waves add together. So here we have wave 1, which is exactly the same as wave 2. If these waves encounter each other in a medium and they add together, the superposition of those waves produces a wave with twice the amplitude. So we added up the sum of the amplitudes for wave 1 and wave 2, and then we end up with a wave that has exactly the same shape with twice the amplitude. So this is called purely constructive interference. Purely constructive interference is when identical waves encounter each other and they add up, and then their maximum amplitudes add up to be twice their original amplitudes, okay? And so then any place where we had a zero quantity, we still have a zero quantity in the resultant, okay? Now let's say we have two identical waves that are flipped to each other. They're same wavelength, same frequency, but they're upside down. One's upside down compared to the other. So here we have wave 1, and wave 2 is the inverted waveform of wave 1. It's just flipped, okay? So when these two identical waves are going to add together, they're going to produce one with zero amplitude, and we call this purely destructive interference. So for example, if I chose these 2 points right here, let's say wave 1 has an amplitude of 1 right here. Wave 2 has an amplitude of -1 down here. So 1 plus -1 gives you 0, right? And we still have 0 at the 0 points when we add those together. So if you have two waves that are completely inverted to each other and then they add together, you produce destructive interference, which means your resultant wave is null, it's 0. So we're going to practice this here. We have two traveling waves that are traveling opposite of each other. So these traveling waves are going to be traveling along the same string, and they're going to encounter each other. They're going to superpose, they're going to add together. So the top wave is moving to the right, or to the left. The bottom wave is moving to the right. And when they encounter each other, we're going to think about the superposition of those waves. Is it constructive interference or destructive interference for these waves, okay? So for waves A, B, C, and D, I want you to think about, if we add those waves together, we add their amplitudes as they're crossing through each other, are you going to get constructive interference or are you going to get destructive interference?